Okay, good morning. Today, what I'm going to do is continue with our discussion. We're going to move on to section 8.4, which is entitled electronegativity. Okay, so yesterday we did 8.3, which was covalent bonding. We're going to take a little bit of a break in a sense from covalent bonding. This is related to covalent bonding, but it's not as directly related. And then we're going to come back and we'll get into covalent bonding in the next section, 8.5. And then we'll look at all kinds of details with that. So let's talk a little bit about electronegativity. So as you recall, we have in electricity and magnetism something called charge. And we can say that something is positively charged in contrast to something that is negatively charged. And this is a property of matter. It's a property of electrons and protons. It's even a property of neutrons, even though neutrons are overall neutral. They are believed to have some inherent charge within them. What we know about particles that have opposite charges is that there is an attractive behavior. There's a force of attraction between the two of them. So if they're able to move, they will move toward each other. And we would say there's an attraction between the two. Now we can also study particles that have the same sign. And these particles will undergo repulsion. So there's two cases here, right? You can have two negatives or two positives. And this is what we would call repulsion. Okay, so in a sense, the atom itself has a balance of forces within it, right? The nucleus, except for hydrogen, has more than one proton in it, and those protons are very close to each other. So they experience a force of repulsion or an energy of repulsion. However, and likewise, the electrons are in atomic orbitals, and we'll look at different types of orbitals later. They experience repulsion between each other as well. But the electrons are attracted to the nucleus, right? And that's an important aspect. The electrons are attracted to the nucleus. And so the question then is, in chemical bonding, does this play out? Does this phenomenon of electric charge play out in terms of the nature of a chemical bond? And the answer is yes, it does. It turns out there's all kinds of interesting aspects that happen. So what we can do is let's take two of these charges. I'm going to take one of them as positive, and I'm going to tie it to the end of a rod and put another charge on the opposite side, which is the opposite charge, right? So one side is positive and one is negative, okay? Now, it turns out that if I then bring up what is called a test charge, so let's make it positive. So here's our test charge. We're just going to test what happens to this rod, this rigid rod with two charges on it. If that rod is capable of rotating, what we would observe is that, and we'll make the test charge stationary, it can't move. What we would observe is that this rod would rotate. So it would just rotate around. We'll attach it like right there so it can't move. It can just rotate. And the positive end of this rod would move away from this positive end, and the negative end would move toward that positive end, right? Kind of makes sense, right? It's essentially moving itself around so that it can maximize attractions and minimize repulsions, right? This negative charge is now closer to the positive, so that's increasing attraction, and this positive is further away from the test charge, so that's minimizing repulsion, right? So it turns out that molecules can, under some circumstances, behave this way. They actually behave like these little rods with charges on the ends. And we call them electric dipoles. So this is called an electric dipole. I'll write it over here. And this electric dipole has a quantity, which is called the electric dipole. And the symbol for that is the Greek letter mu. You pronounce it mu. Just like micro, right? It's the same symbol. This does not mean micro, it happens to be the same symbol. And the micro, or the mu, sorry, the electric dipole is equal to the distance between the charges. So I'll call that D. Actually, I shouldn't use a D, I'll use an R. So we'll call that R. Times the magnitude of the charge difference, Q. Okay. Now this is, I'm going to put absolute value signs over it because it turns out there's a directionality to this. So it's actually an example of a vector. Okay, so at some point we'll talk more about vectors. Okay. So this electric dipole is a quantity that we can calculate, and there are different units that are used for it. But if you think about it, this is length, right? It's distance, right? It's the distance between these two charges. So this is going to have the units of length, which is typically meters, right? That kind of makes sense, right? Now, what's this Q? This Q, don't get it confused with heat, which was lowercase q. Sometimes people use uppercase Q for heat. This refers to the electric charge, the difference in the charge between the two. Okay, so and the units are in coulombs. Okay, so let's say, for example, we wanted to model a hydrogen atom, right? So let's say that we've got your proton for the hydrogen atom. So there's your proton for the hydrogen atom. And then we have an electron over here. Let's say that the distance between the two of them is 5.29 times 10 to the minus 11 meters. Okay, so there's a nice small length. Okay, so there's your distance. Now, what's the charge of an electron? Well, it's negative 1.602 times 10 to the minus 19 coulombs. Okay, so the electric dipole between the, in the hydrogen atom, assuming that those numbers are good, would be the absolute value of 5.29 times 10 to the minus 11 meters times negative 1.602 times 10 to the minus 19 coulombs. Now notice, and that's absolute value, you can get a pretty small number right there, right? It's going to be like 10 to the minus 30. So that's, it turns out that there's a unit called a debye. Okay, so a debye is a unit of electric dipole, and its magnitude is around 10 to the minus 30, right? So if I got 10, somewhere around 10 to the minus 30, it's about a debye. Okay, so that's a detail we don't need to worry about right now. Okay, so the point of this is that even an atom, even a hydrogen atom, right, with one proton and one electron, internally it has a dipole, right? There's an electric dipole because you've got a proton with a charge some distance away from an electron that also has a charge. So you're going to get an electric dipole. Now, the electric dipole is generally represented using a vector. So let me make a new one. We use vectors to represent electric dipoles. Makes sense. Okay, so here's the idea. Suppose I have a positive charge and it's attached to some negative charge. What we do is we represent this dipole using a vector. Okay. Now notice the arrow, the head and the tail, right? An arrow, the vector has an arrow. A vector is represented using an arrow. It has a head and a tail. The head of the arrow should be in line with the negative charge, and the tail of the vector should be in line with the positive charge. Okay, so head goes to negative, tail goes to positive. Sometimes people remember this by putting a little cross on the tail so that you see a positive right there. And then you got the head is the negative, okay? Now, the larger the dipole, so the magnitude of the dipole scales, means gets bigger or smaller with the length of the vector of the arrow. So if you have a small electric dipole, I'll just abbreviate, I'll just call it dipole, you would represent that with a short arrow. If you have a large dipole, you would represent that with a large arrow, a long arrow, right? And again, the negative would be on this end, the positive would be on this end. Okay, so when we do that calculation that I just showed you right there, the length R times the charge Q, I took the absolute value of it just to turn it into a magnitude, essentially, and turn it into a scalar quantity, one that doesn't have a direction. But vectors actually have length and direction, right? So if I were to take this dipole right here, keep it the same length, but move it in this direction, right? So I'm taking this one right here, and I'm moving it over here. Well, now the vector would change directions, right? Now the vector would be pointing this way, right? Right? Because it's going to point towards the negative and away from the positive. So the head is away from the positive and the tail is toward the positive. Okay. So that's just a brief little summary of dipole, electric dipoles, which you would cover in physics, right? But in a sense, we need it a little bit here in chemistry. Because here's what happens when we make certain molecules. If we take a hydrogen molecule, H2, now remember hydrogen is 1s1, right? So that means it has one valence electron. We represent that with the Lewis dot symbol. Since it's H2, that means we have two hydrogen atoms, each has one electron. That pair of electrons can be shared, the duet rule according to hydrogen, right? So now you have that. We can use line notation as well, okay? It turns out that this molecule has no electric dipole. Okay, we call it nonpolar, or we just call it covalent. You'll see both terms out there. Nonpolar or just covalent. Same thing with F2. If I take the F2 molecule, now remember fluorine is element 9, so it's 1s2, 2s2, 2p5. This is the valence shell, so it has 7 electrons. Again, it's in group 7a, so you know right there it has 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. This pair right here can form a bond, right? So now you have a pair shared between both atoms and 3 lone pairs on each fluorine. Okay. Well, we can represent that using line notation as well. Good so far. Single bonds, right? When you have one pair of electrons between 2 atoms, we call that a single bond. If there were 2 pairs, it would be a double bond. If there were 3, it'd be a triple bond. This one also has no electric dipole moment. Oops, let's spell electron right. Electric dipole. So this one is called polar or polar covalent. Both terms are used. There's probably even other terms that are used for them as well. Both of those molecules have no permanent dipole. So you'll hear the term permanent dipole, which means that just means it has an electric dipole. I'm not going to talk right now about the difference between permanent and non-permanent dipoles. You will also see the word moment. So sometimes it's referred to as dipole moment. Same thing. It's just another way. That's a mathematical term, a moment. It's a physics term, a moment. We're not going to talk about that in here. Okay. So let's take a look now. If I combine an atom of hydrogen with an atom of fluorine, notice how I'm just drawing one dot towards the hydrogen there because I've done enough of these and I realize we got to have a chemical bond there, a covalent bond. So here we go, right? Octet rule for fluorine, duet rule for hydrogen. Probably do line notation. 3 lone pairs on the fluorine, okay? It turns out this molecule has a electric or an electric dipole moment. Oops, sorry, I almost put moment in there. Electric dipole, okay? You can call it electric dipole moment, that's fine. Sounds fancier. It has an electric dipole moment. And it turns out the direction is toward the fluorine. The negative end is toward the fluorine, so that's your head. The tail is over here, is toward the hydrogen. So if I rotate that molecule, the electric dipole will rotate as well. So HF has an electric dipole, even though it is a neutral molecule. It has just as many protons as it has electrons. There's no difference in the number of protons and neutrons. There's no difference in terms of, you know, I was going to say something else, but that's not important. It has this dipole. So the question is, why does it have a dipole? And it turns out that some atoms have a greater attraction for valence electrons than other atoms do. Okay, so the issue here is, why does HF have an electric dipole? Okay, and it has to do with this idea of electronegativity, which I'm not going to go into how it's calculated. It's complicated. It's hard to spell words like this. Negativity. Electro, like electron. Negative, right? Electronegativity, right? Density, molality. Okay, so what it essentially, electronegativity says is that each element has an attraction for valence electrons. Every atom has an attraction for valence electrons. Well, arguably noble gases maybe don't, but they have their own valence electrons, so that's not true. They actually do. Okay, so each element has an attraction for valence, but they're not equal. Some elements have a higher attraction than others. So what people have done is they've made hundreds or even thousands of measurements of measuring electric dipoles and combining different elements together to make simple molecules, and measured the electric dipoles and come up with a table called the Pauling electronegativity table. Okay, so what I'm going to do is I'm going to show you, I'm just going to go into Google here, and I'm going to show you a table. And hopefully we can get one that comes up not too difficult, showing advertisements and such. Okay, this is one from an organic chemistry value. From an organic chemistry course. So let me come over here. I'm going to stop share there. And then let's share this one. Okay, so this is what's called a Pauling electronegativity table. You'll notice it looks just like a periodic table, only the values that you're used to, the atomic numbers and the atomic masses, have been removed and replaced with some numbers that have a minimum of 0.7 and a maximum of 4.0. These tables are not universal. Different people have devised their own tables with slightly different values. This one is taken from an organic chemistry course. Now, one of the strengths of organic chemists is they like to have things very simple in terms of arithmetic. They don't like to do complicated math. So for that reason, they like numbers that have maybe only 2 significant digits, not 3 or 4 or 5 or 6 or 7 or 8, right? Speed of light has how many sig figs? 9. That makes it kind of tedious when you enter things into your calculator. These electronegativity values only have 2 significant figures, and they're kind of rounded in a sense. So if you look at hydrogen, the first element that we'll be concerned with, it has a value of around 2. It's not exactly 2, but it's pretty close to 2. As you move down through that column, it gets much smaller. It goes from 2 all the way down to 0.7 at francium. Francium is pretty unstable. I'm not even sure how you measure that. But in any case, notice what happens. Big drop off to lithium to 1. It's down by half. And then it just drops off very, very slowly. These values right here are really close to each other. I mean, arguably, there's a significant difference between 0.7 and 1, but not really. It's a difference of 0.3. It's a pretty small difference. So 2, 1, okay? But notice the pattern. It does decrease as you go through a family. Next column, 1.5, 1.2, 1.0, 1.0. So same pattern. It's going down. But notice within that row, it increased. It went up to 1.5. Okay, this is a pattern we will observe. I'm going to ignore the transition metals for right now. They all have measured electronegativity values, but we are not going to use them in Lewis structures. So this is one chapter where we essentially ignore the transition metals. Okay, so let's move over to the P block, right? The non-metals and the metalloids. In the same period, we have lithium 1, beryllium 1.5, boron 2, carbon 2.5, nitrogen 3, oxygen 3.5, and fluorine 4. No values for these elements up here in the noble gases. What do you notice about that? There's a pattern. There's a mathematical pattern, right? It's very simple, though. 1, 1.5, 2, 2.5, 3. It's increasing by, it starts at 1 and increases by half all the way over to fluorine. Now, again, that's a strength of looking at things from a semi-quantitative way, of not worrying about whether it's 3.12 or 3.04. You get to a very simple pattern. It becomes very obvious to your eye. The pattern is that within a family, within a group number, it decreases as you go down. And as you move to the right, as you move across the period, it increases to the right, okay? There may be an exception every once in a while there. Is there? Sometimes there's one here. I mean, these are all the same, 1.8. So it's not really decreasing, but it's certainly not increasing, right? So, and then again, look at the transition metals. They're a mess. So like it increases here. That's why we're going to use the Pauling table for the first 2 columns, particularly for hydrogen, and then for the P block, which are the non-metals, which are the ones that lend themselves to Lewis structures, okay? So there's your 2 patterns. You need to know those 2 patterns. The highest value is fluorine. We're going to ignore the noble gases for now. There may be an example you have to look at, but we're mainly concerned. These are exotic molecules that have krypton and xenon. It's just a, wow, you were able to make some compound with krypton. That's cool, but it doesn't have much practical use. These elements over here, the highest value is fluorine. The next highest value is oxygen. The next highest value is nitrogen. For those of you that are biology majors, you're aware of these three elements, right? Particularly with hydrogen, HONC, right? HONC, which are the elements that are involved in hydrogen bonding. And the reason they're involved in hydrogen bonding is more complicated than I'm going to go through right now. But one of the primary reasons is the big difference in electronegativity between hydrogen, which is quite plentiful in water, and these three elements having very large electronegativity values. Okay, so most electronegative values are these three here, and then this is significantly smaller. Okay, that leads us into the discussion of determining whether a chemical bond is polar, whether it has an electric dipole moment, or it's non-polar, it has a very small electric dipole. Maybe not zero, but very small, okay? So those are some of the values there. Let me show you now the way we're going to analyze this. We take a chemical bond. So let's take our hydrogen to fluorine bond, represented that way. Notice I'm not drawing in the lone pairs, just because we're not concerned with them right now. They do have an effect on dipoles, but for right now, we'll ignore them. What you do is you write down your electronegativity values from the table, 2.1 and 4.0. And then you take the difference. Now, which one do you subtract from the other? It doesn't matter. You're going to take the absolute value of the difference, okay? If you don't know the absolute value, look it up somewhere. So 4.0 minus 2.1 is 1.9. So that's the difference in electronegativity between those two atoms. And then you use the following kind of guidelines. If the difference is greater than 2, then the bond is ionic. Positive, negative. It's an ionic bond. It's not even a covalent bond. If the difference is between 0.4 to 2, then the bond is polar covalent. And we represent it using a dipole vector, a dipole or a vector to represent the dipole. Okay. And then again, the negative end here, positive end there. So look at this difference, 1.9. I'll come back to that in a moment. If the difference is between 0 to 0.3, the bond is non-polar. Okay, or just covalent, depending on what terminology the people you're talking to want to use or prefer to use. Okay, so a difference of 1.9 clearly puts it in this range here. So we can represent that bond as being polar. You know, it's almost ionic, right? HF is almost ionic. And why did I put the head of the vector above the fluorine and the tail of the vector above the hydrogen? Because with electronegativity, the more electronegative value, that particular atom is the side that's going, the side of the bond that's going to have the negative charge. So there's actually a negative charge here and a positive charge here. Now notice I'm using this little delta sign. You'll see this sometimes. This is called delta. So here's lowercase delta. Here's uppercase delta. Okay. In this context, delta means small. For those of you that have taken calculus, you realize that delta means small, okay? Uppercase delta, capital delta means difference, right? We use that with thermochemistry, okay? So what this means is there's a small difference in charge between those two atoms, and that leads to an electric dipole. So again, if I take a test charge, it doesn't matter whether the test charge is positive or negative, the molecule will rotate if it's free to do so. If it's a solid, it can't do that, right? If it's free to rotate, it will do so that the head of the vector is pointing towards this positive charge and the tail of the vector is pointing away. Why? Because that particular atom is positively charged. So it has to do with how the two elements have a difference in terms of their attraction for the valence electrons. Well, clearly these are valence electrons right there. So really what's happening is those electrons are spending more of their time over here than they are over here. So what that does is it exposes the nucleus here, so you develop a small positive charge. The extra electron density that comes from those two electrons gives you a small negative charge. Okay. So let's take a look then at an example. Okay. Sorry, I'm just kind of reordering this a little bit. Okay. Predicting the relative electronegativity of atoms. Reorder each list of elements in the table below, if necessary, so that the elements are listed in the order of decreasing electronegativity. So you want to put them in the order so that it's getting smaller. So you put the largest one first and then the smallest one. And for this particular example, really what they're doing is they're showing it to you within the same, either the same row or the same column. Okay, so let me close that out and put this up here. Okay, so TE, S, and O. So you just want to look up in your periodic table where those elements show up. Okay. And for this one, group 6A has oxygen, sulfur, selenium, and tellurium. Okay. So in terms of electronegativity, the pattern is it decreases as you go down. So you're going to have the lowest value down here and the highest value up here. Okay. So we want to go in the order of decreasing. So the highest one would be O. The next highest, so I'm going to put greater than. I mean, they may want you to do commas, but I'm going to put greater because that makes more sense to me. So the electronegativity of oxygen is greater than, okay, well then it's greater than sulfur, and then sulfur is greater than tellurium, right? Does that make sense? So you might want to do it like O comma S comma TE. That's perfectly fine, however, what formatting they want. But the point is oxygen has a larger a greater electronegativity than the other two elements, so forth and so on. Okay, so that's fine. Now, what about the next one? The next one is O, F, N. Okay, well, okay, so now what they're doing, you got group 8A, which is neon. You got group 7A, which is fluorine. 6A is oxygen. 5A is nitrogen. 4A is carbon, and then 3A is boron. You can go all the way over and do 2 and 1. But it's these three right here, right? So really, these are the three elements involved in hydrogen bonding, again, for your biology majors, right? I'm sorry. Okay, so the pattern here is that it increases in this direction. If it's in the same row, it increases, right? So this would be the largest right here. So the largest would be F. That would be greater than the O, and that would be greater than the N. Okay, pretty straightforward, right? And then again, you know, what you're going to see when you, let me see if I can find that table again. What you'll see the pattern is that you'll see that the lowest values are all the way over on like francium, right? So francium is the smallest value there. And then the highest is going to be all the way at the top right, which is going to be fluorine, okay? So the maximum values, the highest values are in the top right corner, and the minimum values are the bottom left corner, okay? So that's that problem. There we go. The second type of problem, there's only two problems really in this section. The second type of problem is predicting the bond polarity. So let me bring this one up. In each of the molecules drawn below, one chemical bond is colored red. Okay, so here's a single bond, it's red. Here's a double bond, it's red. And here's a single bond, it's red. Decide whether this bond is likely to be polar or not. Is it polar or not? Okay, that's very simple. You're just going to look at differences in electronegativity, right? If the bond is likely to be polar, write down the chemical symbol for the atom, which will have the more negative charge, right? So just write down the symbol with the negative charge is what they want, okay? So if you look at your Pauling electronegativity chart, hydrogen is 2.1, and bromine was like 2.8, I think, because I think chlorine is 3.0 and bromine is 2.8, or 2.7, 2.8. There's a difference there, right? So 2.8, 2.1, that's a difference of 0.7. That's greater than 0.3. So yes, it would be polar. So that bond is polar. The more negative atom, electronegative atom, is the bromine atom, right? Because it has a higher value of electronegativity. Looking at this bond here, it turns out CO2 is nonpolar, but the individual bonds are polar. So we treat a double bond and a triple bond just like a single in terms of this discussion. And you got carbon, which is 2.5, and you got oxygen, which is 3.5. Well, that's a difference of 1.0. So definitely it's polar covalent, and the oxygen has the higher value. So the more negative atom is the oxygen. These two, big difference here too. Bromine 2.8, fluorine 4.0. That's a difference of 1.2. So that's going to be a polar bond, right? And the fluorine is the electronegative, the one with the higher value. So that's going to be the negative end. Okay. So polar molecule, polar bond. I don't want to say this molecule is bond. We'll talk about this in chapter 9 toward the end of the course. The bonds themselves are polar here. Okay. And that does it for the electronegativity. A lot of background there. I gave about 25 minutes of background and then 10 minutes of doing the problems. So next, what we want to do is we want to start looking at drawing Lewis structures. So we do have a little bit of time here. So we're going to work on drawing Lewis structures. Okay, so the first problem that's shown here, okay, let me actually bring it up so you can see the question. Counting valence electrons in a molecule or polyatomic ion. So this is section 8.5. Okay, so now we're getting into the nitty-gritty of Lewis structures. How many valence electrons are in the nitric acid molecule HNO3? That's very simple. That's sort of your starting point, counting valence electrons, but it is an important thing that you have to do. So let me show you. So HNO3. And I'm going to do it for more than one here. I'm just going to show you. I'll do 3. Okay. What you do is you find each atom. So this is in group 1A. So it has 1 valence electron. Nitrogen is in group 5A, so it has 5. Oxygen is in group 6A, so it has 6. But keep in mind, there are 3 of them there. So here's what you do. You got 1 hydrogen, so 1. 1 nitrogen, so that's 5. But you got 3 oxygens, so 3 times 6. So that you get 24. Okay, so this is counting not the total number of electrons, but the valence electrons. Okay, so group 5A, it has 5. Group 6A, it has 6. So you have 5 plus 3 times 6. But notice this negative, that's an extra electron, so you add 1 more. So notice that the nitrate ion, NO3 minus, actually has the same number of electrons, of valence electrons, as HNO3 does. Okay. This is in group 6A, so it has 6. This is in group 6A, so it has 6. So 6 for the sulfur, 4 times 6 for the 4 oxygens, and an extra 2. Don't subtract 2, add 2. It's 2 extra electrons. So that's what, 32? Now let me show you a positively charged one. Let me show you NO plus. Okay, group 5A, group 6A. So 5 plus 6, but now it's plus, so you subtract an electron. So that would be 10. Okay, there you go. That's counting valence electrons for molecules, anions, and cations. It's kind of cool. All right. So let's come over and look at the next type of problem, which is writing Lewis structures for diatomic molecules. Here we go. Now remember, diatomic just means 2 atoms, and we're just doing really simple Lewis structures here. Just 2 atoms, doesn't get any easier than that. Draw the Lewis structure for H2. So there's 1, that's pretty simple. Draw the Lewis structure for HI. Okay, so that's called heteroatomic, meaning 2 different types of atoms. It's a heterodiatomic atom. Okay, now this one is not a molecule even, it's an ion. So they're being a little bit misleading here. This is not a molecule, it's an ion. So it's N2, 2 minus. Okay. And then the next one is O2, 2 minus. So they're giving you some ions here as well. They're diatomic, so CO, okay. All right, so let's take a look at some of those. I'm not going to do H2, we've looked at that one right there. But we do have CO, we've got HI, we've got N2, 2 minus, okay. So let's take a look at those. 4 electrons, 6. So there's your 10 electrons, okay. 10 valence electrons. So your first step is to figure out how many valence electrons you have. So I'm going to do that first. 1 and 7, so that's 8. So that's 2 times 5 plus a 2, right? You got the 2 negative, so that's 12. So there's your number of valence electrons. Now what you do is you draw a line between the 2 atoms, okay? All right. What is a line? In this notation, a line is 2 electrons. So what we've done by drawing that line is we've used 2 of the 10 electrons. So we only have 8 left now, right? If I use 2 to make that bond, I now have 8. Same here. If I draw a bond, now I have 6. If I draw a bond, let me do it this way. I got 10. Okay, Now what you do is you draw those electrons as pairs. Get one of the atoms that's not hydrogen up to 8. Okay, so see what I did? I drew 3 lone pairs around the carbon. Why did I stop at 3 lone pairs? Because it already has a bond to oxygen, so that gives it 8. But I only used 6. So the other 2 I'm going to put on the oxygen. Okay. So I just distributed those 8 electrons, and now I'm down to 0. So let me review that. What I did was I said I have 8 valence electrons because I already drew a bond in here. So I'm down to 8. I put them as pairs around one of the atoms to get it up to 8. If I had any extra electrons, which I did, I put them on the next atom. If I had 4, I would put 2 pairs on that next atom, but never go beyond 8 at this stage. Once you're up to 8 electrons, I don't mean 8 in terms of the lone pairs, I mean 8 including the bond and the lone pairs. Okay, so same thing here. Now we're not going to put them on hydrogen because hydrogen has a duet rule. It can only have 2, it already has 2. But we have these 6, so 3 lone pairs. Count by 2s, 2, 4, 6. And then same thing here. We've got 10 electrons, we've already used 2. 4, 6, 8. Did I get that right? Wait a minute. Hold on. Sorry. I got 10 to do. 2, 4, 6, 8, 10. Okay. Minus 10 equals 0. You can always check. Make sure your arithmetic is right. We should have had 12. We do have 12 because you count the bond as 2 and you count each lone pair as 2. Okay. Now you go for the octet rule for all the elements that are not hydrogen and the duet rule for the element that is hydrogen. Okay. One of these is already done. It's the center one. This one's already done. Why? If you count up the number of electrons around hydrogen, it's 2. That bond has 2 electrons. If you count up the number of electrons around iodine, it's 8. 2, 4, 6, 8. Remember, the bond is 2. Each lone pair is 2. So it's done. Octet for the nonmetal, duet for hydrogen. Okay. So at the end of this Lewis structure, you should have the same number of valence electrons you started with. You should have a duet rule on any hydrogen and an octet rule on any nonmetal. We had a total of 8 electrons to begin with. We still have 8, and it's done. The other 2 are not done because they don't have 8 around each atom. So here's what you do. This one right here, the problem is the oxygen only has 4. 2 here, 2 here. So you move, this is called electron pushing. Let me get rid of this little arrow here. You push a pair over, maybe you push 2 pairs over until each atom has 8. Okay, I'm pushing it from the atom that has more lone pairs, not the one that has fewer. And look at what happens. So now I'm going to draw a double-headed arrow. This is what we use when we draw different Lewis structures. Those arrows mean that those lone pairs are now bonds. I've converted this lone pair here to becoming a second bond, and I've taken this lone pair here and converted it to being a third bond. This lone pair is still here. This lone pair is still here. And look what happens. Now this one has 8. This one has 8. They're both octet. This one is done. Again, it still has the same number of electrons we started off with. I did not add a bond. I pushed a pair from lone pair to bonded. So how many do you push? You push over as many as it takes to get 8 for each atom. Okay. Each atom gets to count all the bonds between them in a Lewis structure. So if you have 2 atoms with 3 bonds, that's 6 electrons that count for each atom. We're going for the octet. Now this one's a little trickier. So I'm going to bring it down here. Okay, the nitrogen on the left is cool. It's got 8. It's done, right? But the one on the right only has 6. Again, count by 2s. 1 bond is 2, 2 lone pairs is 4. That's a total of 6. Take the atom that has more lone pairs and push a bond over. And here's how this is so cool. This pair in this structure only counts for this nitrogen here, but not this one over here on the right. But if I push it to form a bond, it now is counted by both. And that appears to be what these atoms will do. They will share electrons, converting lone pairs into bonding pairs. And there we go. Again, how many electrons should we have? 12. How many do we have? 12. Be careful with the ions. You use bracket notation, and then you write the charge after. Okay, as a superscript. So 2 negative. Okay, so this is a double bond, right? This one has a double bond. This one over here had a triple bond, right? Carbon monoxide actually has a triple bond. Okay, let me show you one more. Okay. Let's do the peroxide ion, O2, 2 negative. Actually, I'm going to do, oops, sorry. I'm going to do O2, just the oxygen molecule. And then I'm going to do O2, 2 minus. Okay, let's do those two. Okay. Oxygen is in group 6A, so 2 times 6 is 12. Again, this is in group 6, so 2 times 6, but you got this -2, so plus 2, so that's 14. So you assume one bond between the two atoms. See, I'm doing this simultaneously to show you how to go about this. When you do a bond, that's 2. So now we're down to 12 minus 2. So now we're down to 10. So I'm going to write 10 here. Hopefully that'll help. 14 minus 2 is 12. So now we're down to 12. Okay. These are very similar. They're just difference of 2 electrons. Okay. Now you take the 10 and you write them as lone pairs around the atoms. Get one of them up to 8. So see how that one's up to 8 now by adding 6, but I still have 4 to go. So now I'm going to go to the next one. 2, 4, 6, 8, 10, right? Just talking about the lone pairs. You distribute the 10 electrons as lone pairs. Do these all as lone pairs. Okay. So same thing over here, but now we have 12. So these are going to be distributed as lone pairs. See what happened there? I didn't put beyond 3 lone pairs on any of the atoms, because if you did that, you'd have more than 8. You would be violating the octet rule. At this stage, the octet rule is what we're using as our guideline. Okay, this one should have a -2 charge. So I'm going to put it like that. Okay, next step, you check for the octet rule. This oxygen has 8, but this one only has 6. So the one that has more lone pairs, you push a pair over. Okay, so when you push that pair over, you now have an extra bond. Okay, octet for both, right? Octet for both, right? This one we didn't have to push any over because they both have 8. Okay, so there you go. That's how you do those types of structures. Okay. All right, I'm going to end it a little bit early. I'm going to end it right there. Because I want to move on to the simple organic molecules as a separate discussion. So I'll work on that next week. But you're up to doing the diatomics. Okay. if you're really ahead of the game and you want to work on the more complicated simple organic molecules, which again is the same section 8.5, feel free to look at any of the videos from the previous 2 semesters. They're up there as well. So for chapter 8, you can do those ones. Okay. So have a great day and have a great weekend. And I hope things are going well. Take care.